Thank you for being here, and thank you also to the organizers for the invitation to come and present here. You're not going to see any cardiovascular without device modeling from me, because I was told not to show that, even though we have a very large group working on this in my CFD center. I'll mention them in the acknowledgements, but I thought this would be more an overview talk over how CFD is being used overall in industry and government and other areas. So I've titled this State of the Art and Best Practices, and I hope it's not going to be too parochial, but I think it's good at the beginning of a workshop like this to at least go back and think about the fundamentals. Here is an overview of the talk. First, a few acknowledgements, then computational fluid dynamics. You can ask why and then why now. And then the CFD process, state of the arts and trends, because that's going to set the stage of ensuring quality of results, which is really the main topic I was asked to talk about. And then what were the lessons learned over the years, and how can we avoid having the same mistakes being done in a new area of applications. So there's a couple of teams that I work with. I have a large CFD center at George Mason, which is just outside the Beltway here, of fame, having made it to the Final Four a couple of years back. All right? And we're back. So I also work with SAIC, which, if you don't know, this is the largest of the Beltway bandits, as they are called. These are the large government contractors around here, and SAIC is sort of the empire compared to all the other ones. General Atomics, we've done a lot of structural dynamics with them. They're in San Diego. And then we also work with NRL on submarines, torpedoes, and UAVs. Inova, this is the largest hospital here in Virginia. And we have been very fortunate to work with very good neurosurgeons in that area. And at the beginning, it was quite difficult to get their attention, but now we have a meeting every Friday, and they bring new data, and we analyze their cases, and we've built up a database now of over 400 patients, and it's quite nice. And then a couple of university links. So why do we want information, and why do we want insight? Well, we are curious. That's one of our human traits that sets us apart from animals. But there's a very distinct need to predict, particularly in engineering products, and also in intelligence gathering. As you can guess, being from DC, intelligence is a big area. And there's also a need to post-dict. So if we have experimental results, what do these experimental results mean? And I would say that today, at least in my group, 80% of the calculations that we're doing are either in preparation of experiments or trying to elucidate what experiments have shown. Yeah? And this just shows you the importance of CFD in conjunction with experimental techniques. And of course, there's a large area there in forensic analysis. Now, I stress information because information is the most valuable resource of our age. It's the gold of our times. And if we look at a typical product cycle, we start from product definition. This would define the mission of your product. And by the time you come to produce, the curves you have to look at are the following three curves. First of all, what possibilities do you have to change this product along this line? Well, you have an infinite amount of possibilities at the beginning, but when you come to the first prototype and the first prototype testing, the amount of changes you're allowed to make is reduced drastically. The amount of information that you have is only increasing as you get familiarized with your product. And the cost of changing anything that is wrong with the product as you find out more about your product is also increasing drastically as you go along. So the whole aim of this is to try to know as much as possible of the product as early as possible in the design cycle. Okay? So the effect of computational mechanics is precisely that. We want to know as much as possible about what we're trying to build and its consequences and its effects before we actually build it. So if we want to create information or insight, there are really only four ways of doing this. One is the old-fashioned way of doing experiments. Then there is classic analysis. There is computational or numerical techniques. And then data assimilation by using neural nets. But of course, this is only something you can do once you have all the data. So it may lead you to new discoveries, but you must have all the data available. So of these four, the two main contenders are the experiments and the computational and numerical techniques. Now, there are some problems with experiments, and this has been the great benefit that we have doing numerical techniques. And the first one is that it's impossible. Okay? If you're trying to build a nuclear weapon, you can't test it anymore. Okay? If something that you're building as a cardiovascular design is going to imperil the health of your potential patient, you're not going to test it on patients. Yeah? So a lot of these questions, how do I make this better and how do I build it, you can simply not do any other way. So that has led to a lot of developments. And in fact, CFD and many other of these computational techniques were pioneered in environments where you couldn't do experiments reliably. For example, nuclear weapons. They may be inaccurate, and the main reason why experiments are inaccurate is that you have many non-dimensional numbers in an experiment, and you have to match all those non-dimensional numbers in the prototype in order to have that be exactly the same thing that happens in real life. So if we take, for example, I don't know, a missile or a bomb dropping from an airplane, you have the Mach number, you have the Reynolds number, and you have the Fruit number. There's three non-dimensional numbers that you have to match there, and it's incredibly difficult to find a wind tunnel anywhere in the world that will match those three numbers. It's very costly, not only because the wind and water tunnel availability is rather restricted. It takes about anywhere from $150,000 to $500,000 a day to put an airplane in a wind tunnel and measure it. But you may also destroy the object that you're doing or that you're trying to measure during testing. Just think about the efficiency of weapons, you know, a bomb, or you're trying to design a new bunker or a new shelter. Every time you blow this thing up, it may be gone. So another $10 million down the drain. Yeah? It may be untimely, and particularly if you think about consumer goods, time to market is absolutely critical. The car design cycle has shrunk from 7 years, 15 years ago, to only 3 years now. Yeah? So imagine the strain that that puts on trying to get the information as quickly as possible about the product that you're designing. There's a lack of detailed insight because most of the experiments only give you pressure probes and light sheets, or even if you do MRI, it's mainly 2D cuts. You may have a very different resolution in 2 dimensions versus the 3rd dimension. And what is really the worst of all is that most of the experiments give you absolutely no optimization guidance. They tell you this is how it is now, but they don't give you any gradient or any hint as to how to make this better. So why would we use computational sciences like CFD now? Well, we've enhanced the realism. We can now solve many more equations reliably than we could before. If you think about aerodynamics, in the 60s we could solve reliably potential flow. In the 70s, Euler. In the 80s, the RANS. In the 90s, LES. And of course, the idea is to go to direct simulation of Navier-Stokes. And we've also seen a large proliferation of multidisciplinary solvers. I'm not going to talk about fluid structure interaction because a later speaker will cover this. There's been a lot of algorithmic improvements. We've tackled the main difficulties that we were facing in fluid dynamics in the partial differential equations that we were trying to solve. We've reduced setup times, so what used to take months now takes minutes. And there's been a lot of advances in hardware, so we can do these things reliably and in a quick turnaround so that they become relevant. Let me show you a couple of aspects as to what has happened in CFD over the years. In 1959, there was this theorem of Godunov that no linear scheme of order higher than 1 can be monotonicity preserving. This is a devastating theorem, if you think about it. So any scheme that you take that is linear by its very nature, you can take, you know, most of the schemes that were out there at the time, none of these would ever be able to go beyond first order accuracy. And so it took about 10 years before people came around this and constructed nonlinear schemes. And that led to a proliferation of these nonlinear schemes. So in the 60s, if you were trying to solve the simple advection equation, which simply propagates a contaminant or, you know, some concentration downstream, and let's say this is a periodic domain, and this is the exact solution. So I have 3 profiles here. In the 60s, you had two choices. You could either be first order accurate, and you can see what the quality of the result is there, or you could be second order accuracy, and you can see it's much worse than the first order. So that's why many weapons go up to this day are first order if you go to Los Alamos. Right? In the 70s, we had the first nonlinear schemes, and you can see how things improved dramatically. And in the 80s, we finally resolved these three cases using pseudospectral FCT. And let's say the best schemes that were of the ordinary kind were the PPM schemes, which are not bad. You can see there are some oscillations here. We don't reach the full peak, but you only have 3 grid points to get this peak. It's quite difficult. The second problem was the mesh size. What you find in many fluid problems that you have very thin regions or very narrow regions or a very small percentage of the total domain where everything is happening. Boundary layers, shocks, contact discontinuities, shear layers, etc. So the key is, of course, to use a fine mesh to put your degrees of freedom only in that region. So that led to adaptive mesh refinement, and I show you one case here. This is a blast hitting a wall, and you can see here in the mesh that only the regions where the shocks are and the relevant physics is happening, that's where you put your fine mesh. Now, if you count up how much volume compared to the total volume this is less than 1%. So it's the equivalent of 2 supercomputer generations that you're suddenly able to compute. The third one was convergence. As we grew the models, we found out that convergence was getting rather slow. Right? And we know that once we go beyond 10 million degrees of freedom, any iterative solver will beat any direct solver. So what we found out was that iterations required for near-neighbor right-hand side schemes like conjugate gradient or GMRes were of the order of the graph size. Well, the graph size was increasing tremendously, and if you think about an artery, the graph size can go into the thousands. So the number of iterations that you require just grows up linearly. So the idea was to use a series of cosi grids like multigrid, or to use sweep right-hand side schemes like the LUSGS scheme. And I have one case here. This is a landing configuration. You can see here, this is the, I suppose that's the Mach number. These are the pressure contours. This is the eddy viscosity. This is a very fine mesh here with boundary layers and everything on it. And this is the comparison to the experiment. So you can see that you actually reproduce the physics faithfully. And if you take an ordinary scheme with explicit time stepping, you can compute for days on end without reaching anything. And if you combine GMRes with LUSGS as a preconditioner, you can get very quick convergence. So that led to, again, a factor of 10 or 15 in speed up. Now, the biggest improvement that came along that was not our merit was Moore's law. Okay, so if you know that you get a factor of 10 every 5 years, then things become very easy. And what is nice is that as you put more transistors per square inch, you have more register space and more cache, which are the really two important things even today if you're going to buy, an Opteron or a Xeon. That's what matters. And so you have continuing improvements also in the compiler, so you have branch prediction and things like that built into hardware. And then the CPU performance has mirrored Moore's law over the years. Now, prognosis is that this will continue for at least another decade, even though we may not see the improvements on each chip, but then we might go multi-core or something like that. Now, you can see here, this is bringing a little bit of my own personal history. In 1983, if you were doing an airfoil with about 500 to 1,000 degrees of freedom, you were the biggest hotshot that was out there. Okay? As of 2007, if you're not doing 10 to the 9, I'm afraid that's not value for a PhD. Okay? And you can see here the problems, the codes, the algorithms, and the machines on which these were run. But what is important is that this mirrors, in some way, Moore's law. So if we put all these together, the solvers, which give us a factor of anywhere from 10 to 100, the algorithms, again, anywhere from 10 to 100, the hardware, then the compounded gains over the last 20 to 30 years have been of the order of 10 to the 5 to 10 to the 10. Well, the last time something like this happened was during the Cambrian explosion, when suddenly there was enough oxygen so that life could proliferate. Okay? So that's why you're all sitting here. You may not know this, but this is the reason. Okay? So if we do these computer or virtual experiments, why can we do them? They're possible. unless the physics are unknown, but we're now using computer experiments to elucidate physics. So this has become sort of a third pillar of the empirical sciences. It's accurate because it solves the real problem. We don't have to compromise with non-dimensional numbers that we can't reproduce in the experiment. It's cost competitive because we have fast setup times, and any one of the aspects is improving compoundingly, so the algorithms, the software, or the hardware are all going in sync. It's timely. It gives us detailed insights because we get 3D visualization and we can really start asking questions that we can't ask in the experiment. And finally, it gives us optimization guidance, which is very important. So here's just one case. This is configuration line development at Boeing, and you can see here for the 767 and 757 there were at least 77 wings tested in the wind tunnel. As we march on for the 777 there were only 18 tested, and for the 7E7 there's only going to be about 5 tested by the time the aeroplane flies. The improvements have been even more dramatic with the engine nacelle integration. There's been a rather dramatic reduction here. You can see that 2 of the engines that are mounted on the 737 were never tested before they were mounted and flown. Everything was done with CFD. And you're flying in those airplanes, so you might want to think that when you fly back. Now, if you look at the number of wind tunnel hours that were used in designing these different aeroplanes, you can see that we've had a leveling off at about 10,000 wind tunnel hours. And the main reason is not that the wings have become less complicated. On the contrary, we are testing less wings, but the wings are more complicated, but the main reason is CFD. So, having said this, what is the state of the art and what are the trends? And I was asked to give sort of an overview talk, so I'm taking advantage of this. So let's talk about engineering first. It's used extensively. It's used everywhere. Okay? You may not know it, but in many of the sectors that I've listed here, we are way beyond the so-called missionary phase. In fact, we are, I would say, in many areas past the commercial off-the-shelf phase. It's embedded. It's part of the everyday process of designing, analyzing, forecasting, doing forensic analysis. It's there, and it's there to stay. Okay? We've had now the experience that CFD vendors are part of the process or the supply chain. So the expectations from the users are rising continuously. If you are in the car industry, basically you now have an in-house culture that is formed. You have people with experience that have done this for 20 years that can mentor the next generation, and new features are demanded from the user base. People will come to you and say, if you don't have this in the next 2 years in your code, I'm going to switch to the competitor. So there's a tremendous pressure on these vendors to continually improve and exceed the expectations of their customers. We have a very healthy mix of CFD packages out there, so we have what I would call a deep genetic pool, just in case there's any eventuality happening. There's a very large commercial market for this. There's government and open source. There's in-house industry, lab, and university codes. And basically the penetration is going to happen by niching. This is the way it's going to be, and it's only natural. So you're not going to have in the future the code that can do everything. You're going to have the code that can do this particular area as best possible, which is the same thing that happens experimentally or in a medical lab. You don't have a lab that does everything, or you don't have a wind tunnel that can measure all wings and all airplanes. You're going to have certain wind tunnels that do things better than others. And the same is going to happen in CFD. Okay? Now, CFD packages offer many levels of fidelity, all the way from potential code to DNS, and that carries with it the risk of oversimplification. And this can have very costly consequences. So this is something to keep in mind. Now, all of these CFD packages have a very high degree of maturity. They have very nice GUIs, very nice preprocessors, grid generators. They not only solve the flow field, but the adjoint, which is very useful to determine errors, to know where to refine, if you're doing optimal shape design, things of that nature. They all have adaptive refinement modules. They can move bodies or attach to CSD code, link to optimization packages, and so on and so forth. And I just want to mention the training and support and the benchmarking, because if we look at quality assurance, that's very important. If we look at the physics, in all of these packages, Euler and Navier-Stokes equations are very well established. They have fast and reliable solvers. I've mentioned 3 or 4 areas where really the front is moving towards. One would be if you're trying to do acoustic fluctuations with a compressible flow code. Think about jet engine noise or something of that nature. Basically, the fluctuations you're looking at are 10 to the minus 6 of the ambient pressure, so you need a code that is better than 10 to the minus 6 in accuracy. Well, there is no such code out there. Yeah? So you need to rewrite the equations and use specialized codes for this. If you think about combustion, the main problem is the many species that you have. It's like a 4-dimensional problem, because you may have 60 or 120 species. Just think about your car engine, and most of the parameters are not known. Then you think about multiphase. There is a whole notion of computational bubble dynamics and free surface and spray, where a lot of the physics are still unknown. And if we think about blood, in particular plasma, you may want to think about the bridging of the continuum and the atomistic scales. I talked about the numerics. I won't belabor this point, and the hardware. But I just want to say that current PCs in 5 years, we can solve about 10 million elements on this laptop. In 5 years, we're going to solve 100 million elements. That should do very well for a lot of the device modeling that is being discussed here. And if you think about supercomputers, we're going to be at about 10 to the 11 in the next 5 years. If you look at the validation and verification, there are many test cases that are out there. Most of the commercial codes are running 24/7, 365, their battery of test cases before every new release. There's a very large library of test cases for most of the commercial codes that are out there, and every new release must pass the test. So there is a certain amount of quality assurance that is being done in commercial packages, and there's a lot of training opportunities out there. So now, how do we ensure quality? If we want to answer that question, let's review again the CFD process, try to identify the weaknesses, and then try to see what we can do. So if we look at CFD as a process, it's really a chain. And a chain is only as strong as its weakest members. So let's look at the parts of the chain. First of all, we have engineering. That's the reason why we want to do this. Then we have physics, which tells us which are the relevant phenomena, which are the possible approximations, what are the PDEs or the ODEs that describe this. And I've just put down the Navier-Stokes equations there. Then we have to go into mathematics, which tells us what are really the properties of the partial differential equations that we're trying to solve. What kind of solutions can we expect? And then based on those solutions, we will determine which numerical scheme is best. Then we have to code this. So that brings up algorithms, software, and hardware. Then we have to visualize the results. And it's not just ways of seeing and optimal algorithms, but really trying to take this to a higher level so that these can be tools of discovery. And then finally, we have the users. And I'll come back to this towards the end of my talk, but this is a point that you should never underemphasize. You need a lot of benchmarking and quality assurance. You need an educated and motivated workforce, and you have to counteract things like the non-invented here syndrome, which is very prevalent out there. It's a bit like AIDS, but it's there. Okay? So that's the whole chain. So if we want to ensure quality, the first question that we have to ask is, what are we computing and what is relevant? And I can tell you from having a bloodied nose over many years that this takes about 3 years to answer if you go into a new field. You think you know the answers. It takes about 3 years to find out what is really relevant. And what is the accuracy that is required and achievable? Again, that takes experience. There is no easy answer for that. As far as the physics are concerned, what are the relevant physical phenomena? What is it that I'm really looking after? And what constitutes a proper description? And it's not just whether I'm solving Navier-Stokes, but whether I have the proper rheology. Is really non-Newtonian flow important for the blood flow that I'm doing? Is fluid structure really relevant? Am I just kidding myself, or do I really have to do this? So these are the types of questions that you want to answer there. Then we have to look at classic numerical analysis. What are the admissible solutions and what are the numerical schemes that we should be using for that? And what is the numerical error? Have I coded things properly? And is the algorithm running as expected? Having a code that runs worldwide on many platforms, I can tell you, you can run something 150 times and you put it on a new compiler and a new hardware platform and things break apart. It happens. So do we have the proper tools to gain insight? That's the main question for visualization. And as far as the users, are they trained and motivated? And then we come to the CFD run. In the CFD run, we have the input part here. And of course, we can ask ourselves, how sensitive is the final result to this input? Have I done that properly? Then I have to generate the mesh, run the CFD code, visualize the results, estimate the errors, and this may be an iterative loop. There may not be a first shot answer to this. So, the questions that we can ask here are, is the geometry properly defined? How accurate do I have to be in my geometry? Are the boundary conditions set properly? Well, particularly if you think about patient-specific modeling, this is a really big question. Are the physical parameters set properly? Again, try to do fluid structure interaction for patient-specific models. What is your elasticity model really? And what are the parameters that you're going to use for this particular patient? Is the grid resolution sufficient? Can you visualize the errors or estimate them properly? And are the runtime parameters set properly? So, as far as the overall process, I have some more questions here, and they're mainly based on sensitivity. So how sensitive are the results that I'm after? And this really depends on the engineering question. What am I after? How sensitive are these results to the geometry? How important is a corner, a curvature, the right geometrical definition? How sensitive are the results to boundary conditions? So if you think about an airfoil, if I've missed my angle of attack from what I estimate to what happens out there by 0.1 degree, what is the drag increase that I'm going to have? Am I going to incite flutter? Am I going to incite any other dangerous phenomenon that might be lurking out there? Am I close to a bifurcation point? How sensitive are the results to physical parameters like the turbulence model, grid resolution, and then how sensitive are the results to the runtime parameters, and here in particular the time step? What you find is that if you reduce the time step, you might see new physical phenomena. Okay. That's my shopping list of questions. Now, let me give you a few possible answers, and I've said some answers because I don't have all the answers. Okay? So, typically, you work with engineers and you try to establish a dialogue between the code developers all the way from the beginning towards the end users. And so you may find that for many people, integral quantities are perfectly all right. If you're designing an airplane, lift and drag is perhaps all you need, or a car. But for many people, local quantities are important, and not just any local quantities, but a local quantity at a certain particular place. So there is no universally perfect mesh. If I want to have lift and drag, I may need a very different mesh, and I may have a very different sensitivity to input or physical parameters than if I want to have a local quantity at a certain point. What is the accuracy that is required? Well, I've listed a couple of sectors here. And if you are in the aerospace, particularly in the commercial aerospace, 1% more drag is a deal breaker. So you need to know your drag to at least 1% if you're going to convince a potential customer to buy your airplane. If you're in the car industry, 5% lift to drag is absolutely acceptable. Now it's a bluff body, the flow fields are not streamlined, so even to get to a 5 or 3% drag prediction is quite difficult. So people have accepted this only because we can't do better. There's also another reason why they accept this. 5%, this is within the tolerance of the user or the driver, and really what you want to know with the drag and the lift is how stable is my car and how do I have to do my gears. So if I'm off by 20% and I have a 5-gear system, then of course the gear changes will have to happen at different velocities. So that 5% is something I can live with. If you think about blast, I may not even know the mixture of the explosive that has been used in a terrorist attack to a certain degree of accuracy. So I cannot estimate the TNT equivalent, which means that 5 to 10% peak pressure is already extremely good. And if you think about chemical engineering or all the other possible industries, food industry, all the other industries that have a lot of variability, then engineering will tell me what is the accuracy that I need. Okay? Then you have to look at the manufacturing tolerances. What is the point in having the geometry defined to 10 to the minus 6 if I can only manufacture to 10 to the minus 1? Okay? So perhaps you are, as the saying goes, barking at the wrong tree there. Now, as far as the physics is concerned, the only answer that I have is work in collaboration with experiments and work long term. Okay? Because this is a moving target. You may think that you have the right model. You go back to the experiments, you compare, things don't work out, you have to go back, and you may find that things that you have completely overlooked, that you never thought were important, are really the relevant ones. This area here, I would say, is very well in hand. There's a lot of emphasis from applied mathematics, but there's always surprises. Now, as far as software and hardware, the proper coding is done. The hardware you compare to exact analytical solutions, because you know what your partial differential equations are. Or there is what people are using a lot, the so-called method of manufactured solutions. So you give a solution that you say, this is my exact solution. Then you plug that solution into the Navier-Stokes equations or whatever equations you're solving. That will produce a source term on the right-hand side. Then you run your code with that source term, and you should be able to reproduce the solution that you put in. That's the method of manufactured solutions. There are some problems with boundary conditions and things of that nature, but they're being worked out. Then you have to quantify your numerical errors. And in fact, many societies like the AIAA or ASME will not accept a paper that has computational results if you cannot quantify your grid independence and your tolerance. So the way that you do this is that you make the mesh twice as fine and then 4 times as fine, etc., until you burst your computer resources and you say that's my converged result. Now in 3D, and I review a number of these papers, sometimes you find people say, oh, we doubled, the number of elements has gone up by 2 and there were no changes. Well, guess what? The factor of 2 in 3D doesn't do anything. You have to be at least 8 times finer before you really see a difference. This can also be done with adjoints on the same mesh, and that's why I mentioned the adjoints before. And many of the codes actually compute and output and then allow you to visualize the estimated numerical errors, which is extremely useful for users. Then, based on experience and collaboration with practitioners, you can come up with guidelines for best practice. For example, in the aerospace industry, you will never build a mesh that is going to compute drag on a wing if you don't have a Y plus resolution of 1, okay, in the boundary layer. And then there are norms and accepted standards as to how many points you want in the boundary layer and how they are distributed there, and then how many points you want if you go around the corner or something of that nature. And as far as checking whether the algorithm is running as expected, the best thing that has transpired over the years is what is called extreme coding. You basically have a test battery and you send that out at night to hundreds of different machines that have different operating systems and different compilers, etc. You recompile everything, you run your test cases, you bring that back, and you have an automatic comparison algorithm. As far as the visualization, we typically display the results with an uncertainty level. And this is sort of a recursive loop. Do I have the proper tools to gain insight? Will I code something? I look at it. Can I ask new questions with this? If not, I will have to go and code this back. And at least in our group, we write everything ourselves, and this has been a huge benefit because you can start, tinkering and asking questions and show me something that if you try to rely on commercial codes, the loop is much, much slower. I mentioned users because the user training is really the key to successful use of CFD and user motivation, of course. I mentioned this graph before. And if you look at the CFD, how do I ensure that the geometry is properly defined, that the boundary conditions are properly set, that I have the right physical parameters, that the grid resolution is sufficient? And really, the answer to this is GUIs. Right? So visual, visual, visual. Try to have as much visual input for the user as possible. Try to alert him to possible mistakes. That has, over the years, transpired as the best way of handling that issue. And really, grid resolution is experience or some of these guidelines that have transpired over the years, and then comparison to experiments. And have my runtime parameters been set properly? Well, you can do a lot of damage with the codes and the options that are out there. So really, preprocessors and careful usage of the codes and experience is really the answer to that. Now, do we have standards? Yes, we do. There are AIAA standards for validation and verification. There's a whole set of guidelines for this that you can download. The same for the ASME. And there is also this started out as National Association for Finite Element Standards, NAFEMS, started out in Great Britain, but it really has mushroomed in Europe. It's not so much in the United States, although it's also being used. And basically these give guidelines as to which finite elements work and how reliable they are and how many you should use if you're going to do modes of a certain kind, etc. Then there are all these compute-offs where you define a problem and you either do it blindly or you do it in collaboration with the experiments. And the idea is that you have a well-documented experiments that is compared to CFD runs. And there are many, many instantiations of this exercise. In the aerospace industry, we have the AIAA drag reduction workshop. There is the EcoMass hypersonic corner, and countless others. If you can see here, every one of the areas has its own set of standard benchmarks that they go through. Okay. All I want to say is that some of these can be quite expensive. If you are going to participate in the AIAA drag reduction workshop, you will have to put a person for at least half a year, so that's about $150,000 that you have to put down. So it's a rather expensive club to be participating in. Why? Because they require at least 3 meshes for each one of the cases, and you have to do the whole drag polar. So you're talking of the order of 100 runs if you're going to participate in that set of benchmarks. Yeah, I'm almost done. Okay. What are the lessons learned? Well, this is sort of my conclusions. It's firmly established in many sectors. It's the modus operandi in very large sectors of industry. It's essential for insight and optimization. I've talked about the enablers. As far as observations from 25 years of experience, capability is much more important than speed. Obvious. Problem size correlates with physics. The more physics I put in, the more expensive it gets. Right? You can take that both for airplane aerodynamics, but also for structural mechanics. Engineering codes have many options, and most of them are scalar, if you think running parallel. And oversimplification can be extremely costly. So it's better to wait a little bit longer for the right result than waiting a very short time for the wrong result. Now, successful codes or successful programs require a long-term commitment. This is not something that is going to happen overnight. It needs institutional memory. So whether this is NASA or whether this is FDA or whoever wants to take the lead in this, unless you have a long-term commitment from a central agency, it's very difficult to make this happen. In the codes that you pursue or the programs that you pursue, do not try to solve the world, just solve the particular problem that you have at hand. You commit to a problem, you don't commit to an algorithm or technique. You want to solve this particular device or this particular problem, and you have a clear plan to get there. You need very close collaboration to experiments because you want to have a gradual build-up of confidence from both sides. And basically, I don't want to finish with Churchill's words, but this is blood, sweat, and tears. Yeah? This is a lot of hard work, and it takes many years. I have a truck case here, but I mean, even though you have all the resolution there, you can see here the difference between an unsteady and a pseudo-steady run, and this was something that really had to do with the experimenters, otherwise you wouldn't find this out. This is my final slide here, and it's really a slide to NSF more than anybody. CFD packages have a very vast range of models and options. So a user that wants to use these packages intelligently will have to take all of these decisions. What does it mean? It means that the possibility of doing something wrong is also immensely large. Okay, so unless you have a qualified individual, you're not going to get the right result. You know, we always have this dream that we're going to have a moron running these things. Yeah. These are non-linear physics. They require really qualified people. And so even from a device manufacturing point of view, you might want to go back to your HR departments and really get the right individuals and as NSF train the right people. So American youth, where are you? Okay, that's my message here. And so I'll stop with that. Thank you very much.
Again, tour de force of CFD. So why don't we take a couple of quick questions, and then we still have time for our coffee break. And then, yeah, go ahead, Larry.
Scaling of resources. The previous speaker and you, particularly you at the end, you talked a little bit about the resources. And we saw spectacular successes for the aerospace industry, for the automotive industry. The last time I checked, the medical device industry had 12,000 registered manufacturers.
Yes.
But the resources available for making any one decision or any set of decisions by an individual manufacturer is proportionally less. So they have a much more restricted ability to use these kinds of technologies for their own decision making, just because of the resources available.
Yes.
How do we bridge this gap between spectacular successes with huge scales down to successes at the level at which we need it in medical devices?
Okay, this is a very good question, and it mirrors something that we have seen in the smaller industries, the smaller manufacturing industries like food industry or mold filling, plastic, things of that nature. It was to these people for many years impossible to adopt anything like CFD or structural dynamics, but the proliferation of low-end workstations, the ease of use of the packages, and really the industrialization, the super niching of packages to a particular niche or to a particular user has led to a huge proliferation in this. I mean, you say there are 12,000 devices. There are, I think in Europe alone, something like 24,000 small foundries and mold filling, small melt, These people had never used anything like CFD in their life. Why? Because they only have one or two or perhaps three engineers that are actually designing this. So the critical mass there is extremely small. So you either outsource it, okay, which you can do, or you have to bring down the price and the ease of use and the specialization to these people. Now, if you have 12,000 device manufacturers, I'm sure there's a market out there and somebody's going to do it in the near future. And at least that has been what we've seen with the mold filling or the plastics business or whatever. I mean, I think it's going to happen automatically because if you can show that you can generate the revenues, people are going to do it. So I don't know if I've answered your question. For the large, spectacular cases that you saw, of course, there are deep pockets, but I would contend there are also very deep pockets in the device manufacturing. I mean, if I look at the revenues of Boston Scientific or Medtronic, I think there are deep pockets out there. Thank you very much.